How do you do it?
Okay, so welcome back to mechanics. Let's see, I have copies of the problem set here for those of you who have not picked it up yet. Do most of you just print it out? Yeah. You do, because I printed out exactly the right number, and I still have like 20 of them left. So, okay, that's fine. I'll just print out fewer in the future. Only other announcement is that the exam has been scheduled, so the midterm will be whenever we decided it was, which was, I believe, February 16th. And it'll be during class time, so 105 to 225, and it'll be in room 103, which is the bell room. So that's right next door. And that'll be good. It'll be a little quieter, so that you don't have to listen to people eat lunch while you take the exam. Okay, yes. I wasn't going to make fun of you, but yeah, you did forget to email me. So, okay. Well, maybe what I'm going to do is just attach this dog to my chair so that he doesn't run off. No, you want him to run around, but you have to promise to keep the door closed so that he doesn't go and steal people's lunches. Okay, good. Okay, so last time we continued. Okay, I know the dog is fascinating, but let's pay attention here. So last time we continued our discussion of oscillators. Okay, come here.
There we go.
This is the problem. He'll calm down in just a minute, I promise. Okay, so last time we continued our discussion of oscillators. We continued our discussion of oscillators, and in addition to the simple harmonic oscillator, which obeys the equation of motion q double dot plus omega squared q is equal to 0, we considered two variations on the simple harmonic oscillator. Namely, we considered the damped harmonic oscillator, which has, in addition, a damping term proportional to q dot, which is determined by a quality factor q, and we also included the addition of a driving term, which would represent the effect of a force which is continually pumping energy into the system. And we remembered from differential equations that the general solution to the system is given by a sum of two terms. So the first thing to do is write down the general solution to the homogeneous differential equation, where we take the driving force to be equal to 0. That is just given in terms of exponentials if we write down the complex solutions, or if we take the real part, it was given by an exponential prefactor along with some sines and cosines that describe the oscillation. And in addition, if we have a driving term, we need to add to this a particular solution to the driven differential equation. And we discussed two different ways of finding such a particular solution. The systematic way of finding a particular solution was to use Green's functions. So if we define the Green's function, g of t and t prime, to be the response of the oscillator to a kick of unit impulse at t equals t prime, then that means that this Green's function obeys the differential equation of the damped harmonic oscillator, but with the addition of a driving force, which is a delta function at t equals t prime. And then having solved for the Green's function, The general solution with an arbitrary driving force is found by performing an integral. We integrate t prime from minus infinity up to t of this Green's function, t of t prime, multiplied times f of t prime. So the Green's function represents the response of the oscillator to a kick of unit impulse at t equals t prime, and then we integrate that over all times before t in order to find the response of an oscillator to an arbitrary driving force. And the reason why we could use the method of Green's functions to determine a general solution to this differential equation was because the differential equation was linear, meaning that the right-hand side, the left-hand side of this differential equation here was linear in Q and its derivatives. For a nonlinear differential equation, it would be impossible to use the method of Green's functions to write down a general solution in the presence of a driving term. And so that's one reason why linear differential equations are so much easier to study than nonlinear systems. And that's one reason why it's often so useful to make the approximation where we're studying a system only for small excitations around equilibrium, where the dynamics is approximately that of a harmonic oscillator. Because in that regime, the equations of motion are linear, and we can use complex solutions, we can use Green's functions, we can use all of these other tricks. So, are there any questions on that, which was the material we covered last time, before I continue? Okay, so if there are no questions, perhaps I can just finish by giving you one final example of the study of a harmonic oscillator. And so, in this example, I will consider driving a damped harmonic oscillator with a driving force that is sinusoidal. So the driving force will be periodic in time, and I'll just take it to be a constant times sine alpha t. So here, alpha is the frequency of the driving force. So just to remind you, there are really three different frequencies in the game now. So the differential equation that we are trying to solve is q double dot plus omega squared q plus omega q dot over the quality factor is equal to the driving force sine alpha t. So just so that you don't get confused, there are three characteristic frequency scales in this problem. There's omega, which is the original frequency of the undamped, undriven oscillator. There's the quantity that I called omega prime last time, which is omega times the square root of 1 minus 1 over 4q squared, which is the frequency of the damped harmonic oscillator. And finally, there is the driving frequency, which I called alpha. Okay, so the homogeneous solution to this differential equation is exactly the same function that I wrote down for you last time. So it's easy to write down the generic homogeneous solution to this differential equation. And those homogeneous solutions all decay in time. So the particular solution that we find to this differential equation will represent the steady state behavior at late times. So we want to find Q particular, which is the steady state behavior at late times. once all of the homogeneous parts of the solution have decayed away. Remember that they decay exponentially in time. So for times that are very long compared to these frequency scales, omega and omega prime, only the steady state solution will remain. So now there are two ways that I could proceed. The first way of finding a solution to this differential equation is to simply use the Green's functions that I worked out last time and integrate them against this driving force sine alpha t. Now that's all well and good. The integrals that you get at the end of the day are rather complicated. So instead what I will do is I will use the second method that I described for constructing solutions to the differential equation. Namely, I will just guess. So in particular, what I would like to do is I would like to use the following trick. So the trick that I will use is that rather than writing my driving force as F naught sine alpha t, I would like to consider a complex driving force F, which is F naught e to the I alpha t. And once I do that, then my differential equation, q double dot plus omega squared q plus omega over q dot equals F naught e to the I alpha t, will have complex solutions. And the real part of a solution will describe the response to a driving force, which is F naught cosine alpha t, and the imaginary part will describe the response of an oscillator to a driving force F naught sine alpha t. Just using the fact that e to the I alpha t is cosine alpha t plus I sine alpha t. The reason I do this is that exponentials are so much easier to deal with than sines and cosines. So by using the fact that my equation of motion is linear, that the left-hand side of this equation of motion is linear, I could just take the real and imaginary parts of this equation of motion and see that they give us the response of an oscillator to a cosine alpha t and sine alpha t driving force, respectively. So is that clear? Good. Okay. So having done this, I would now like to make a very simple guess for the solution to this differential equation. So the guess that I would like to make is that Q is equal to a constant, which may be complex, times e to the I alpha t. So remember, I'm looking for a complex solution to this differential equation, and only at the end of the day will I take its imaginary part to find the response with a sine alpha t driving force. So if I take this ansatz, if I take this guess for Q, and I plug it into the differential equation, then the nice thing about an exponential is that whenever you hit it with a derivative, you just get that exponential back again with a constant. So the differential equation then just becomes, from the q double dot term, we have minus alpha squared. And from the omega squared term, we have plus omega squared. And then plus I omega alpha over q, all times q e to the I alpha t, has to be equal to F naught e to the I alpha t. Sorry, that's a q naught there, not a q. So then we immediately see that we have a solution, provided Q naught is equal to F naught divided by minus alpha squared plus omega squared plus I omega alpha over Q. So this is the complex amplitude of the oscillation. So what we conclude is that the solution is an oscillation with frequency alpha and complex amplitude Q naught, given by this expression above. So just to remind you, the norm of Q naught will give us the real amplitude of the oscillation, and the phase of Q naught will give us the phase of the oscillation. So in order, it's perhaps useful to write those down a little more explicitly. So let me just write this as, so whenever you have a complex number in the denominator, you just multiply the complex number by the complex conjugate of the denominator divided by itself, and you get minus alpha squared plus omega squared alpha squared over Q squared times minus alpha squared plus omega squared minus I omega alpha over Q. And then from this, it is straightforward to compute the real... Yes, did I make a mistake? I'm sorry, I forgot to square it. Squared. Yeah, I squared that one. I already squared that guy. Thank you. Sorry about that. So from that, it is easy to read off the amplitude and the phase of the oscillation. So, for example, the phase of the oscillation we just write Q naught is A times e to the I phi t. And then phi is given by the inverse tangent of the imaginary part of Q naught over the real part of Q naught. So that is alpha omega over Q times omega squared minus alpha squared. So if we were to plot that, so this describes the phase of the oscillation. So if we were to plot that as a function of alpha, then for very small alpha, we would be calculating the inverse tangent of 0, so phi would be very close to 0. And for very large alpha, we would be calculating the inverse tangent of infinity, so phi would be very close to pi. And as alpha increases from 0 to infinity, phi will increase monotonically. So this is the phase shift.
Should there be a minus 1 in the inverse tangent as well?
Is there a minus?
Minus alpha omega.
Yes, there's a minus there. Sorry, I'm not being very... I'm never terribly careful with my minus signs, if you haven't noticed. So this is the phase shift of the oscillator relative to the driving force. And you can see that when alpha is very small, phi is going to 0, and the two oscillations are in phase. If we have an oscillator whose natural frequency is very high, and we drive it with a very low frequency driving force, the oscillator will just track the driving force. When alpha goes to omega, the denominator of this formula diverges, and phi goes to pi over 2. So in this case, the oscillations are out of phase by 1/4. So when the driving frequency is equal to the frequency of the undamped oscillator, the response of the oscillator will be exactly 1/4 of a period behind that of the original oscillator, of the driving force. And finally, if we drive an oscillator by a very rapid driving force, phi will go to pi, and the response will be precisely out of phase by half a period. So, for example, if the driving force is a cosine, then it will be precisely out of phase the response will be precisely out of phase by pi. Hopefully I've drawn that correctly. Okay, so that's the phase lag of the oscillator relative to the phase of the driving force. What about the amplitude? So the amplitude is just the norm of Q naught as a complex number. So that is given by, I'll just write it down for you again. F naught over the square root of F naught over omega squared minus alpha squared quantity squared plus alpha squared over omega squared Q squared. So, for example, if we wanted to compute the amount of energy in the oscillator, then that is proportional to the amplitude squared, and roughly speaking, as a function of frequency, we'll have some sort of bell shape, just given by the graph of the amplitude squared. And this is a famous shape which is known as the Lorentzian line shape. And you can check that this is maximized So to compute the value of the driving frequency for which this is maximized, all you do is you take this amplitude or this energy, you take the derivative with respect to alpha and set it equal to 0, and what you'll find is that it's maximized when the driving frequency is omega times 1 over 1, omega times the square root of 1 minus 1 over 2q squared. And this is known as the resonant frequency of the oscillator. So I should point out that this resonant frequency is different from the undamped frequency omega or the damped frequency omega prime, which had a 4 instead of a 2 there. in that expression. So you can see that for a damped oscillator, there are really three characteristic frequencies that you need to keep in mind. There is the frequency without damping, the frequency of an oscillation with damping, and the resonant frequency, which is the frequency where the response of the oscillator is maximized with a driving force. Are there any questions on this? So you probably encountered most of these in your previous discussions of oscillators. Am I correct in understanding this? Yeah. So Fergus has a question, but he never asks good questions anyway. Are there any other questions aside from plaintive whines from my dog? Okay, I'm sorry. Some of you in the back can't necessarily see it when it's this low, so I keep trying to remember to lift it up. Probably. No. Usually when someone asks a question saying that I've done something wrong, I assume they're correct. Occasionally I'm correct, though. Any other questions? Okay. So oscillators are fun. Oscillators are good. We love oscillators. But it's time to consider a somewhat more complicated system. So the simple harmonic oscillator and its cousins, the damped and driven harmonic oscillators, are the simplest example of one-dimensional dynamical systems. And we saw that in the case of an oscillator, the equations of motion were linear and the solutions were very easy to write down. In fact, it turns out that every one-dimensional system is, in a sense, exactly solvable. And in a sense, what I would like to do now is argue to you that there is an exact solution to every one-dimensional mechanical system. But of course, only in a certain sense. And the solution will not, in general, be nearly as simple as the solution to the simple harmonic oscillator that I described for you before. So let's consider a dynamical system with one degree of freedom that I'll call Q. And the dynamics of the system will be determined by a Lagrangian L that depends on Q and its derivatives. And I would like to consider systems where the Lagrangian is time independent. So whereas a general one-dimensional system would have a Lagrangian that could include some explicit dependence on time, such as would be the case, for example, for a driven oscillator, I would like to consider systems where the only dependence of the Lagrangian on time is implicitly through the degree of freedom Q and its derivative. So, as we learned, the fact that the Lagrangian is independent of time, this means that the energy, or the Hamiltonian, which was given by dl by dq dot times q dot minus L, is a constant. It is independent of time. And in fact, you can check that the equation of motion d by d dt dl by dq dot minus dl by dq equals 0 explicitly implies that E dot is equal to 0. Why is this the case? Well, remember that the Lagrangian is the difference of the kinetic and the potential energy. And if we assume that the kinetic energy, that the constraints of the system are time independent, then the energy is the sum of the kinetic and potential energies. And as I believe I went through previously, one can then show that the equations of motion will imply that the energy is conserved. Yes, was there a question? No. So this, in many cases, allows us to understand the solutions to the equations of motion completely explicitly. So consider the case where the Lagrangian is just the usual kinetic term, 1/2 q dot squared minus v of q. Of course, I could consider systems where the Lagrangian is a more complicated function of q and q dot, but this will be a simple example that will serve to illustrate the point. So in this case, the energy is 1/2 q dot squared plus v. So I can then go ahead and solve that equation for q dot. And we see that q dot is given by the square root of 2 times the difference of E and V. So here, E is a constant which depends on the solution to the equation of motion, but is independent of time, and V is a function of Q. And because I've taken a square root, this equation is solved whether I put a plus or a minus sign in front of the square root. And this equation determines the motion completely. In particular, if I have a solution with a given energy E, then if I know the position at any time t, then I can compute the time derivative of the position at that time using this equation. And then I could integrate this to find the full solution to the equation of motion. Now, that's not to say that I could explicitly do the integrals, but at least in principle, I could write down an integral expression for the solution to the equations of motion. Just to be a little more explicit, I can manipulate this equation further. So I have dq over dt is plus or minus the square root of 2e minus v. So dt is plus or minus dq over the square root of 2e minus v of q. Or integrating both sides of this equation, t is plus or minus the integral dq over the square root of 2e minus v of q. Just to be a little more explicit, the time it takes for the system to evolve from a position q0 to another position q1 is given by the integral from of q from q0 to q1 dq over the square root of 2 e minus v of q. So this explicitly allows me to solve for t as a function of q. Now, when I say explicit, that doesn't mean that I can necessarily do this integral for every possible potential v. So for the case where v is proportional to q squared, this is an oscillator, and what you will get is a logarithm or arc sine or arc cosine when you do this integral. But in general, by doing an integral of this sort, then I can solve for the time it takes to move between one position and another position as a function of Q0 and Q1, as well as the energy of the solution. And sometimes, if you're lucky, this can be inverted to find Q as a function of T, but not always. So this may or may not be an easy integral to do. And even if it is, it may or may not be invertible. To find Q as a function of T. But in any case, what we have seen here is that for an arbitrary potential, the time it takes for the system to move between two given positions is given just by some completely explicit integral. And even if we don't know how to do this integral explicitly, we can often learn a lot about the system by studying this integral. And sometimes we don't even need to study the integral. Sometimes we just need to study the statement that Q dot is plus or minus the square root of 2e minus v. And just by looking at that equation, you can learn a lot about the dynamics of the system. So, for example, let's imagine that I have a potential V of Q which looks like this. Then, in order to determine the dynamics of the system, we should start by labeling the equilibrium points. So there's a stable equilibrium point right here. There is an unstable equilibrium point right here. And then, in order to specify the state of the system, I will need to tell you what the energy of a solution of the equation of motion is. So, for example, if I have a solution to the equation of motion whose energy E is below the minimum energy here, which I could call E naught, then if E is less than E naught, if E is less than E naught, I think, is he tangled up over there? Okay. Go wander around. Stop whining. Okay. I'm sorry about that. If E is less than E naught, then what does the dynamics of the system look like? Well, what the dynamics of the system looks like is at late times, Q is all the way over here, and then it rolls up the side. It rolls up the side of the potential before coming to a stop right here where Q dot is equal to 0, and then rolling back down. So Q goes to infinity at early and late times, before coming, and it has a turning point at the point where Q dot is equal to 0. Which, by this equation here, is just where E is equal to V. So that's the case if the energy is less than E naught. So if the energy is larger than E naught, but less than, let's call it E1, which would be the value of the energy at this unstable maximum of the potential, then there are two possibilities. Then one possibility is that Q goes to infinity at early and late times. Or the other possibility is that Q oscillates around the stable minimum, which we could call Q1, where the size of the oscillation is determined by the value of the energy. And finally, if E is bigger than E1, then Q will go to infinity at early and late times, but we'll have a turning point which is somewhere up here. So is that clear? You probably went through similar exercises in your previous encounters with mechanics. Am I correct in understanding that? Yes. Good. And it's often very useful for considering the dynamics of one-dimensional systems to just draw the potential and understand what the dynamics of the system could possibly look like as a function of energy. So, for example, let's do another slightly more complicated example. So let's consider, for example, the pendulum. So in this case, the Lagrangian, as we worked out earlier, is 1/2 ml squared theta dot squared plus mgl cosine theta. Here, theta is the angle that the pendulum makes with vertical. And so the potential as a function of theta is just given by a cosine. So, as you can see, this has an infinite number of stable minima, where theta is an even multiple of pi. So that would be here, here, and so forth. So this would be theta equals 0 and theta equals 2 pi. And it has unstable minima, where theta is equal to an odd number times pi. So here, for example, is pi, 3 pi, and so forth. And so you can see that there are two qualitatively different types of trajectories that the pendulum can take. So if the energy of the pendulum is between the minimum value and the maximum value of this cosine, so if the energy is larger than minus mgl, but less than plus mgl, then what we have is an oscillation around a stable minimum. So, for example, if the energy is equal to, if this is the energy here, then the pendulum will just oscillate around the stable minimum. On the other hand, if the energy is larger than mgl, then theta will just be monotonic, which is to say theta will always either increase or always decrease. This just corresponds to the case where the pendulum has so much energy that it just keeps going in the same direction for all time. And so the pendulum would spin forever. Is that clear? So, in understanding the dynamics of one-dimensional systems, it is often useful to describe the dynamics in terms of phase space. So, did you guys encounter phase space in your earlier mechanics classes? You probably did, although you didn't call it that. So, phase space. So what is phase space? You certainly encountered the words. You've heard the words phase space before. You never were told exactly what it is. So let me tell you exactly what phase space is. Phase space is the QP plane. If we have a dynamical variable Q and its conjugate momentum P, then we can think of the plane formed by Q and P. So in the example of the pendulum, this would be the plane theta and the momentum conjugate to theta, which is m L squared theta dot. So practically, this is the plane which is given by theta and theta dot, or Q and Q dot. So why is it useful to think about the QP plane? Well, because energy is constant, the system will evolve along curves of constant energy, or constant E, in the QP plane. So, for example, for the pendulum, the energy is the sum of the kinetic energy 1/2 ml squared theta dot squared and the potential energy minus mgl cosine theta, or in terms of the momentum p theta, that would be 1/2 ml squared p theta squared minus mgl cosine theta. And we know that if we were to draw a picture of the motion of the system in the theta p theta plane, that motion would lie along a curve of constant E. So because of that, it's useful to draw a picture of phase space, which is the QP plane, or the theta p theta plane. And then on this plane, we can draw the lines of constant energy. So let me first draw what the lines of constant energy look like. And then explain the diagram to you. So, of course, the plane is infinite, so I won't draw the whole thing, because that could take all day. So this is what the lines of constant energy look like in the p theta plane. So the lines where energy is less than mgl are given by closed contours on this plane. So for example, if this is the point theta equals 0, then there's only one point where p theta is equal to 0 and theta equals 0, that corresponds to a curve where the energy is exactly equal to minus mgl. So that describes a state of the system where the pendulum just hangs down and doesn't oscillate at all. Or if I have an energy which is between minus mgl and plus mgl, then the system will follow one of these closed curves here, where theta oscillates periodically between a value that is less than pi and larger than minus pi. Whereas on the other hand, if the energy is larger than mgl, the curve of constant energy is not a closed curve, but is one of those open curves that I've drawn at the top and the bottom half of the diagram. So you can see that there are two types of curves where the energy is larger than mgl, one of which has p theta larger than 0. That means theta dot is positive, and so the pendulum is swinging in, I guess it would be a clockwise direction, where theta is continually increasing. And the other curve down here describes the pendulum swinging in the counterclockwise direction. And finally, I should note that these sort of singular trajectories, which form the boundary between those trajectories that are closed and those which are not closed, are precisely those with energy equal to mgl. And because those trajectories separate two different types of trajectories, they are known as separatrices. So such a trajectory is known as a separatrix, and the plural of separatrix is apparently separatrices. So these are curves of constant energy. And if we wanted to, we could draw little arrows along these curves which describe how the system evolves in time. So for example, on the open curve at the top, the system would evolve to the right. On the curve at the bottom, the system would evolve to the left. And for these closed curves, the system will evolve around them in a clockwise manner. And so the fact that energy is conserved means that once you draw the lines of constant energy on the QP plane, all you need to do is specify the initial position and velocity of the system at some point on the phase space on the QP plane, and then you can use this diagram just to follow the evolution along that curve of constant energy. Are there any questions on that? Hopefully that's more or less clear. Yes? Negative time? Well, time is just a parameter that we use to label the state of the system. So it could be positive or negative, however there's no, there's a particular time which we call t equals 0, but that's just a choice of how we label times. We could call it t equals 1,000,000 if you like. So positive or negative time doesn't really mean anything. Yeah, I don't know if I answered your question, though. Any other questions? Yes?
On the separatrix, does it go in a circle or does it go like that?
Well, the separatrices are interesting. So why don't you tell me what happens on a separatrix? Any guesses? Who thinks that the system oscillates on a separatrix? Don't be scared. Okay, no, but we're voting right now. Yeah. So what is the separatrix? So on a separatrix, what the system looks like is, so if this is a part of the potential that goes between, say, pi and 3 pi, say these 2 points here, then what does the system look like as it evolves along a separatrix? Well, it starts up here with an energy that is exactly equal to MGL, and it's sort of a very kind of precisely balanced configuration where the pendulum starts up here hanging exactly up, and then it swings down and it goes back exactly up. And it actually takes an infinite amount of time to get all the way back up to the top. So it doesn't actually oscillate. It rolls down and then it goes back up and takes an infinite amount of time to get back up to the other end. So if you want to, I invite you to prove that to yourselves. So I gave you earlier the formula for the amount of time that it takes a system to evolve between two positions as a function of the energy. So set the energy equals to MGL and compute the integral as you go along one of these separatrices. And you can show that integral diverges, so it takes an infinite amount of time. So physically, it is impossible to precisely tune the initial conditions of your system so that you're lying exactly on a separatrix. They tend to be very unstable, and so you'll tend to be either slightly above or slightly below a separatrix. That's why we tend to not see a lot of pendulums that are hanging upside down. Okay, because it's a very difficult thing to do. But if you were very, very skilled and very precise, you could get something that is almost there, and so the pendulum could balance there for a while before eventually tipping off. That's a good question. So another point that I should make is that, as you can see from this diagram, just a second, near a stable minimum, the constant energy curves look like that. They're sort of closed orbits. They will be exactly circular for a simple harmonic oscillator. So very close to a stable equilibrium, the orbits will be exactly circular. And then as you move away from a stable equilibrium, the orbits will be not exactly circular, but almost circular. So for a simple harmonic oscillator, the orbits are circular. And near a simple harmonic oscillator, the orbits are almost circular. So the curves of constant energy are nearly circular. So I invite you to prove it to yourself that the constant energy curves of the simple harmonic oscillator are circles. Actually, I suppose they're technically ellipses if you, with the squashiness of the ellipse depending on the frequency of the oscillator. I don't think squashiness is a word, but I think you know what I mean. What is it? Eccentricity of the ellipse, yes. Or we just call it squashiness. And near an unstable minimum, rather than looking like circles or ellipses, the constant energy curves look like hyperbolas. So the separatrices are these straight lines here. Whereas the other curve, the generic curve, will be some sort of hyperbola. And so just as for the stable excitations around a simple harmonic oscillator, you can prove that the orbits are circles. For the unstable excitations of around an unstable fixed point, you can show that the curves are hyperbolas. And that is reflected in this diagram that I drew above. where you have circles around the stable fixed points at 0, 2 pi, and so forth, and hyperbolas around the unstable fixed points at pi, 3 pi, and so forth. So in your problem set, which I will hand out next class, you will have plenty of practice with drawing such diagrams on phase space. So are there any questions on this before I can continue? Yes, you had a question. Yeah.
In that diagram over there, what does theta equals 0 correspond to stuff like 0 angular momentum? Because isn't that's where the pendulum
yes.
is most, like, that's where it's...
Yes. The pendulum is not moving there. When theta is equal to 0, well, okay. When theta equals 0 is this line here, okay? So p theta could be anything when theta is equal to 0. You need to tell me what the energy of the system is. If the energy is minus mgl when theta equals 0, the pendulum just sits there, and we're at this stable point where there's no angular momentum, there's no momentum, there's nothing. But you could also have a case where theta is between mgl and minus mgl, which would be something like here. You could have a case where the energy is exactly mgl, where you would sit on a separatrix. Or you could have a case where the energy is really big, where you would sit on one of these open curves. Good question. There was another question over here that did you have a question? Okay. Yeah. Okay. No other questions? So, as I emphasized, although we can explicitly write down an integral for the time it takes to evolve from one point to another, we can't always do that integral exactly. So, for example, we could use the formula that t to evolve between one point and another point is plus or minus the integral between q0 and q1 dq over the square root of 2e minus v to write down an integral expression that would tell us how long it takes for the pendulum to evolve or to swing from one point to another. So for a simple harmonic oscillator, the amount of time it takes for the oscillator to move through one entire oscillation is independent of the amplitude of the oscillation. That was a consequence of the linearity of the equation of motion. However, for the pendulum, the amplitude, the period of an oscillation depends on the amplitude of the oscillation. That's why, even if you keep winding a grandfather clock, it will eventually go out of time, because the excitation of the pendulum around the stable minimum is very close to a simple harmonic oscillator, but it's not exactly a simple harmonic oscillator. And so the period of the pendulum, which is what the clock uses to keep time, actually is not exact, actually changes as the pendulum winds down and the amplitude decreases. So, if we wanted to compute the period of the pendulum as a function of time, we would have to perform a very complicated integral of the sort that I have written here. Such integrals have a name. They're known as elliptic integrals. You can look them up in your favorite table of integrals or something like that. It would not be particularly exciting for anyone if I were to spend the next 20 minutes telling you about the theory of elliptic integrals. So instead, what I would like to do is just consider an approximation. So let's consider the Lagrangian of the pendulum, and let's expand it around the stable minimum at theta equals 0. So we will have the usual kinetic energy term, then the potential energy term, MGL cosine theta, and let's just take that cosine theta and expand it around theta equals 0. So we will get, so what is cosine theta expanded around theta equals 0? Well, there's a constant, which is -1 in this case. Well, okay, no, it's 1, isn't it? Sorry, there was a minus sign out front. So there's 1 minus 1/2 theta squared plus, who the hell can remember? 1/24, I think it is, theta to the 4th, plus so on and so forth. So that 1, of course, doesn't matter. That just corresponds to adding an overall constant to my Lagrangian. And as you showed in your problem set, adding a constant to the Lagrangian doesn't change the equations of motion. That theta squared term tells us about the first terms in the equation of motion expanded around the stable minimum at theta equals 0. So that'll give us the simple harmonic oscillator behavior. And then that theta to the 4th term will give us the first correction to the simple harmonic oscillator behavior around the stable equilibrium. So if we just keep this theta to the 4th term in the equation of motion, then this is known as the anharmonic oscillator. So the harmonic oscillator is when we only keep the quadratic terms in the Lagrangian, or the linear terms in the equation of motion. And that was when the oscillator was harmonic in the sense that the period was independent of the amplitude. And the anharmonic oscillator describes what happens when we have a more complicated system. So, for example, the quartic anharmonic oscillator is the case where the potential is the usual q squared term for the harmonic oscillator plus a correction term, which is conventionally given by a parameter epsilon times q to the 4th. I could, of course, imagine a q cubed term that would be the cubic anharmonic oscillator, or I don't know, I could take a 5th term, which would be the quintic anharmonic oscillator, and so on and so forth. So let's now try and compute the period of the anharmonic oscillator. So remember that the time it takes for the pendulum to move between 2 points. So let's say that the potential looks like this. So it has a q squared plus a q to the 4th part. And let's try and compute the amount of time it takes for the pendulum, for the anharmonic oscillator to go through one period of oscillation. So that's the amount of time that it would take to go from, if I start at some initial value of q, say q max, and then the pendulum will swing down, go back up to another value over here, where q is minus q max, before turning around and going back up to the turning point at q equals q max. So the amount of time it takes to do that will just be 4 times the amount of time it takes the pendulum to go from q max down to 0, right? So it goes from q max down to 0, then 0 to minus q max, then minus Qmax back to 0, then 0 back up to minus Qmax. So the time is 4 times the integral from 0 to Qmax dq over the square root of 2 times E minus the potential, which was 1/2 Q squared minus epsilon over 4 Q to the 4th. So we now just need to do this integral and to write it as a function of Qmax. And what is the energy here? Well, the energy, because we're looking for a solution where the pendulum or the system is at rest at Q equals Qmax, the energy is just the potential at Q equals Qmax. So this is the energy, which is 1/2 Qmax squared plus epsilon over 4 Qmax to the 4th. And so now the period of the oscillator is given by this integral. And it will be a function of the amplitude of oscillation, which is to say it will be a function of Qmax. So what I would like to do is now do this integral for you. Again, this integral can be computed explicitly, but we will only be interested in the case where epsilon is relatively small, so I will not bother to do this full integral. Rather, I will just use an approximation where I treat epsilon as being very small. Any questions before I do this computation? It's clear why this is the correct computation to do to compute the period of the anharmonic oscillator. I multiplied by 4 because of the following. So if I want to compute a full period, which is the time for starting at Q equals Qmax to undergo one full oscillation to minus Qmax and then back to Qmax, but it's easier for me to do the integral just from 0 up to Qmax. So yeah, I did that. I could have done twice the integral from Qmax to minus Qmax, but it's easier, I don't know why I did it this way, just because I feel like it. So that's just a way of simplifying the calculation. Okay, so let's do that. So let's first change our parameter that we're integrating over to make our life a little simpler. So let's define x to be the ratio of Q to Qmax. So then t will be 4 times the integral from 0 to 1 dx. So then we have an x squared. So we have, let's see, the e minus 1/2 q squared. So there's a 1/2 Qmax squared minus 1/2 q squared. The 1/2s cancel the 2 out front here, and then we divide everything by Qmax, so we get a 1 minus x squared, because we've changed from the x to the Qmax variables. And then we get plus a constant, which is epsilon Qmax squared over 2 times 1 minus x to the 4th. That 1/2 comes because I have 2 times a quarter, and the Qmax squared just comes keeping track of the Qmax squareds. So I'll just let epsilon prime be epsilon times Qmax squared over 2. And then what I would like to do is work in the approximation where epsilon and epsilon prime are very small, so that I can Taylor expand this expression. And so I'll get t is 4 times the integral from 0 to 1 dx over the square root of 1 minus x squared. And then I Taylor expand this guy, and I get minus epsilon prime, because that's what I called epsilon Qmax squared over 2. And then there's a minus 1/2 because I'm Taylor expanding something to the minus 1/2 power, 1 plus x squared. One plus x squared being 1 minus x to the 4th over 1 minus x squared. Now I could just change variables again, letting x being sine of u. Then this will be 4 times the integral from 0 up to pi over 2 du, because dx will be cosine of u, and the square root of 1 minus x squared will be cosine of u. So the dx will just, over the square root of 1 minus x squared will just become du of 1 minus epsilon prime over 2 of 1 plus x squared. So 1 plus sine squared u plus higher order terms. So the period, well, there's the integral of 1, which is pi over 2 times 4 is 2 pi. Right? That's a good sign. When epsilon equals 0, I get a period of 2 pi. I'm studying, I defined my anharmonic oscillator so that the frequency was equal to 1, so that it's a good thing that I found my period was equal to 2 pi, because it takes 2 pi to go through one oscillation. And then there's this next term, so there's 1 minus epsilon prime. Okay, I can do this. There's a 2, there's oh Christ. Okay, let's stare at this for a second. So 2 pi minus 2 epsilon prime times the integral from 0 up to pi over 2 of 1 plus sine squared u. The thing that you should always remember about the integral of sine squared and cosine squared is that sine squared and cosine squared average to a half. So whenever you integrate sine squared over cosine squared over a period, you always get a half. So that's 3 halves, 1 plus a half times pi over 2. Did I get that right? I think I got that right. So this is 2 pi times 1 minus 3/4 epsilon prime plus higher order terms. So what we see is that if epsilon is greater than 0, then the period of the anharmonic oscillator is shorter than that of the oscillator. Physically, that makes sense, because if epsilon is positive, then the potential is steeper than that of the simple harmonic oscillator. So as you roll up the side of the potential, you get more energy, and so your velocity increases. On the other hand, if epsilon is less than 0, the potential is gentler, and the period is longer. So, for example, for the pendulum, you can compute epsilon just by Taylor expanding cosine theta around theta equals 0, and it was minus 1/6 because I had a 1/24th coming from the Taylor expansion of cosine, and then I defined a factor of 4 in my definition of epsilon, and so the period of the pendulum is 2 pi over omega, which is the normal period of a simple harmonic oscillator, now restoring the factor of omega that I had set equal to 1, times 1 plus, so epsilon epsilon prime included the value of the amplitude of the oscillation, so the maximum value of the angle squared over 16, and of course with a minus sign. plus higher order terms. So this tells us, as a function of the angle of the oscillation, that the pendulum takes a slightly longer time to go through one period than... Sorry, there's a plus sign there. Right. Good. Because there was a minus sign here and then a minus sign there. Okay. Okay, good. So that's what it should be. So the pendulum takes a slightly longer time than a simple harmonic oscillator to go through a period. And so, in fact, all of the people who have built grandfather clocks knew this formula, even though they didn't know that they knew this formula, because it's one of the things that goes into keeping a grandfather clock accurate. So I should probably stop here. Are there any questions before we end? I'm sorry my dog was such a pain in the ass. I think I probably won't bring him again. He was kind of annoying. All right.